When a conventional bomb goes off, it relies on chemical reactions. Molecules are rearranged to release energy, but the individual atoms themselves remain untouched. The binding energy holding a nucleus together is several orders of magnitude stronger than chemical bonds, yet it remains stable under almost all terrestrial conditions. This stored energy is inaccessible unless the nucleus itself is compromised. The challenge for early 20th century physicists was finding a physical mechanism to disrupt that nuclear stability and release the energy held within the core of the atom. By the 1940s, researchers identified two distinct methods to achieve this, one involving the heaviest elements and another using the lightest. These two reactions are the basis of modern nuclear weaponry, where the massive output of the first method is a trigger to ignite the second. The first method is nuclear fission. It utilizes heavy, unstable elements like uranium-235 or plutonium-239. Fission is the process of physically fracturing a heavy nucleus. When struck by a neutron, the core splits into smaller fragments. This releases a massive burst of atomic energy. The reaction radiates outward from the moment of fracture. This mechanism powered the first generation of atomic weapons, deployed in the 1940s, contained inside heavy steel casings like the one seen here. While fission was a massive leap in destructive power, it has physical limits. You can only pack a certain amount of heavy fuel together before it becomes too unstable to manage. To increase the scale of these weapons, engineers had to look for a completely different reaction that worked on a much smaller scale. This second method focuses on the lightest elements on the periodic table, specifically isotopes of hydrogen. Nuclear fusion is the process of joining together two of these light nuclei to form a single, heavier one. This chart compares the energy yield of the two reactions. For the same amount of fuel, the fusion process produces a significantly higher yield than fission. However, because atomic nuclei naturally repel one another, merging them requires levels of heat and pressure found only in the cores of stars. This presented a massive technical challenge. To trigger a fusion reaction on Earth, researchers had to find a way to generate those extreme solar conditions inside a portable device. The solution was to use a fission bomb as the catalyst. The heat and radiation from a primary fission blast provide the environment necessary to trigger a secondary fusion stage. In a modern thermonuclear weapon, the process begins in a primary stage, where a fission reaction is detonated inside the casing. The energy from that first blast is channeled downward to compress the hydrogen fuel in a secondary chamber, igniting the fusion reaction. By using this two-stage process, weapons could scale far beyond early designs, resulting in the massive, multi-ringed devices seen in modern arsenals. The result is a fireball that reaches tens of millions of degrees, producing a thermal pulse and blast wave powered by the same physical principles found in the center of the sun. Modern thermonuclear weapons are complex, two-stage engines. They use the total output of a standard atomic blast merely as the ignition sequence for a second, more powerful release of energy.